Good afternoon, everyone. Good evening. This is the last week's doubt clearing session on the subject NT principles and applications of building science. So I'm just waiting for a few people to join. Now let me start again going through a run through of the last week's portion, which covers mostly the acoustics and lighting design concepts. Basically, we have to, as I said before, we have to move a building like do building design and have an understanding how building functions over the occupancy period, the whole lifetime of the building. Uh, we have to maintain certain comfort criteria inside the spaces according to the activity. Actually, all these parameters they also depend on the type of activity that is going through in a particular space because uh, industrial building it requires type of space comfort requirements and kitchen or a classroom with each space defines its own comfort requirements and accordingly we have to design. And when we look into this week we are going to look into acoustics and also lighting design. One thing about acoustics is acoustics the sound uh, level of speech what a person or like a group of people in art the space should provide uh, certain conditions so that if they intend to have a conversation the space should allow them to converse without any hindrance. Or if it's another space, imagine it's an hospital space, the room has to be as silent as possible and here we have to think in terms of rather than looking this acoustics just in a room we have to look how to control the noise from the outside also because uh, these type of spaces which require more silent environment it's about more controlling the noise from outside and on the other case if you have a music auditorium or a oratory speech where a huge group of people like 300 to like around 1,500 capacity hall we have mostly what the purpose of the auditorium is whatever the sound coming from the stage to clearly be communicated with the audience who's sitting in the front row or who's sitting in the back row everyone should be able to receive the sound clearly. So previously we covered about what is sound and how sound is measured and what are the various parameters associated with sound, how we measure sound, what is the unit. Generally, we measure sound at using sound pressure level and its unit is decibels. And these are the various terms that we put into sound power, which is the actual amount of sound is given as an output from a source. And sound intensity, pressure, and exposure, these are all various parameters in looking into how you receive sound from a source in receiver's perspective and how it travels. Last week we covered the relationship between these terms, sound power, intensity, and we can check the previous week's reference. Key concepts. One more thing what I want to mention was last sound almost equally acts like light. Only thing is the general concept of sound and light is functions the same, but only thing is their actual detailed properties they vary. Like in terms of finding the actual light source from a distance, it also uses inverse square law. And even here in sound, here also we use inverse square law. And this example, if it was shown using uh, for a given sound power, what will be the sound intensity level at a distance. This is found using the formula. First, we have to find the sound intensity using the formula is equal to watt by 4 pi r square. Or what is the sound power and r square is the distance or the radius of the receiver from the point source. Here we are having a omnidirectional point source, and the sound intensity level is found using this logarithmic formula. L1 Li is equal to 10 log I by 10 to the power minus 12. And as per the inverse square law with doubling of distance, the sound intensity level from the point source drops by 6 decibels. And also, previously also seen how, if imagine if there are like two sound sources of same sound intensity, what will be the resultant sound intensity level at a particular distance. If we have like same point sources, the sound intensity level will increase by 3 decibels for every doubling of sound. And also, to find the resultant sound, we have to compare between each sound source's sound intensity level and have to understand that if there is more difference between the two sources, the higher one has to be selected. If the difference is very low, we have to add uh, from a range of 0 to 3 maximum. If you have same sound sources with same sound intensity levels, you can add it 3 decibels to that sound source and the resultant sound can be taken. But if the difference is pretty high, like imagine there is a difference of 9 decibels between one sound source and another sound source, we have to just take the higher sound sources sound level to find the total sound level. So you can check this. And also there are many parameters and criteria we use in acoustics. One of this is sound level equivalent, where the sound level for a given space is measured over a time period. Like sound L equivalent is the time integrated linear equivalent sound pressure level. So using this, if you want to find what is the sound level, like what is the peak over a period of time, and how, and what is the general sound level. All these things you can reduce using this L equivalent, and these L10, L50, and L90 values will be a good indicator. Like example, L10 is the sound pressure level exceeding 10% of the time. It means that there will be some small spikes during the occupancy. The imagine there's a period of occupancy. Over time, you have certain time periods where you have very high sound levels. So this will fall under L10, and L90 will be like the base sound level. That will be like generally background. So imagine if you let us take one room, the kitchen as an example. In kitchen, most time period it will be silent and not silent. Like it will have some noise of like mixing and cooking food and stuff. But there will be some certain periods where you use high heavy equipments like grinder or mixing. That time there will be a peak in sound. Those will imagine those heavy equipment operation, they fall under this L10 category. That will result in like around 90 dB, but L90 might be around 40, 45, 50 decibels. And this and all I have covered previously, like uh, how to find the sound intensity level at using with the directional and non-directional source, and we cover this directivity as the from the sound source, which there are like immediately there are different planes from the sound source depending on the number of planes and the actual due to the concept of directivity, the received sound level will be high. And we can see if there is a horizontal plane, there is an increase of 3 decibels. There's an increase of 3 decibels. And if we have like two planes from the source, then we are increasing 3 decibel. And if we have a, if you imagine the sound source at the corner of room, the source of the sound will increase by 9 decibels due to the concept of directivity. And also, we have to keep in mind that there is different sound level associated sound pressure level associated with different frequency. For a given source, you will have a sound output of varying frequency, and each frequency set will have its own sound pressure level associated with it. This image you can see for breeding. I was just covering the previous section because acoustics is a continuum. Last week and this week it will be the continuing thing, and also we'll look into overview of lighting and lighting design. Lighting we didn't cover much in this module. Lighting is also a larger concept. Here we have just given basic introduction. I'll just cover two key concepts and then I'll show you some example aptitude questions. With that we close. If you have any doubt also, please you can ask me. Moving further, as we are speaking, looking into the sound and sound frequency, this image is a very good example. Yeah, sure, you can ask. You have thermal design, sir. Yeah, please. Is it regarding the calculation of U value or? which one? You can mention it in, or you can switch on your mic and ask also. I will connect my. You want to ask now? You can go ahead. Do you plot? Okay, the you're saying the plot size, the area that you are choosing. So basically, like not just the plot, you cannot just take one single plot and find how it will affect. You have to find out what is the surrounding local boundary conditions also. Maybe I'll just give me a second. I'm just finding a cable. Okay, इसका cable आपने देखा micro USB. Yeah. So here we imagine you have this plot and it's the whole building you are going to build. If you have like attended the like if you have listened to the first set of lectures, basically we started with the whole solar geometry, then we covered into climate, then we looked also into microclimate. So the plot what role it plays is the microclimate. One major thing related to building design, you have to look in terms of what and all are the surrounding buildings or the landscape around it. Imagine there might be a lake nearby the plot. Usually it won't be, it is a rare case. Or you can say an nala will be running through near the plot. And there might be open space. So here the main thing what you have to consider is generally we go with climate level analysis. Then we have to look at microclimate and the building surrounding built spaces. All these things you have to incorporate. Definitely, what you said, the plant does play a big role. So we have to choose according what is the there will be generally the climate and microclimate doesn't vary much, but there will be a minimal difference that you have to look into. And as you mentioned, the site associated surroundings they will majorly affect in terms of one thing. If you want to guess, you can guess. The first thing we looked into solar geometry majorly. First we it affects the solar radiation that is coming onto the site. Imagine there are like two floor, you are imagining you are going to build a two-floor building, then there are like high-rise building near your plot, definitely it will affect the solar radiation, and as it will cast shadow at different time periods according to the direction the site belongs to. Imagine this is the north direction, and if the site is located in a like beyond the Tropic of Cancer, like above the Tropic of Cancer, it means that it won't receive any solar radiation from the north side. Mostly the south, from the south, you will receive solar radiation. Like, and this radiation, like from the east during the noon time, it will be around 3 p.m. So if you have a buildings, or I imagine you have trees, the trees will provide shade in that region. So it will definitely affect the thermal performance. And one more thing is the drainage you have to look into. These are like next level other type of functional aspects that you have to look into. Majorly, one thing is this solar radiation what I spoke about. Next, if you have a water body nearby, definitely there will be uh, a relatively higher relative humidity. So this another aspect, and also due to if it is a dry climate due to evaporative cooling, the temperature might be low also, and also due to this solar radiation and presence of trees, since the place will be more shaded, it will also might decrease the temperature around, or if there are like many buildings around due to heat island effect, the temperature in that particular surrounding might be higher than uh, if you go away from the, particularly if you go away from the if it is a city, if you move away from the city, you might see around a drop of around like 2 to 4 degrees Celsius just because of the UHI. And I'm just speaking about air temperature, like the surface temperature drastically will just change, and so all these aspects you definitely have to look. Okay, microclimate. So microclimate is basically due to the presence of microclimate is basically the climate that is being created by the presence of the site and surroundings. The site and surroundings will have its own small it will create a small change in the climate, like in weather, day-to-day weather conditions. Imagine you generally if you Google search what is for your current location that you belong to. If you Google search what is the weather like, it might be showing that the weather temperature is around 32 degrees Celsius for that current time period. But if you actually measure using a dry thermometer, the temperature that you measure will definitely vary. Most cases it will vary. It might be around 30, 31, or it may go to 33 also. This is because of the microclimate. So basically, what is microclimate? Okay, fine. Definitely, the trees and plants they also will create a change in the microclimate. One thing is they block solar radiation in that region. Next is if the trees and plants are very small, it doesn't have a significant height relative to the building, they will definitely create this change in relative humidity. Like they will increase the water content present in the air due to because of the plants. They absorb water and then they transpire. And do this transpiration process, the surroundings will have relatively higher humidity. So in this way, there is a change in the microclimate. That's what. If you have more doubt, you can ask. Let me proceed with today's uh, thing. Next, moving on, going back to acoustics part. Previously, thanks, Philip. We discussed about sound and various concepts related to sound, and today we will look into the certain criteria associated with building acoustics. Uh, one of the one thing is this noise criteria, which I just discussed earlier, like each phase depending on the activity, what type of sound is present in the surrounding or in the space, you can determine. Okay, okay, Surbaju, he asked again about this is related to thermal. He asked that okay, why we are placing kitchen in southeast direction. Basically, southeast direction people also keep in north east southeast also. It's basically it doesn't have like direct implication, but one main thing is generally what people consider like southeast most time period you will get morning time period, you will get some radiation falling onto the kitchen. So since kitchen is most likely you prepare food and then the space to make it well lit and receive proper lighting throughout the working time period, and also solar radiation falling on the surfaces, it kind of create microbes. It will kind of avoid microbial infection on surfaces. All these things they kind of play a part. There's not much. It's basically it's a previous what ancient type of concept. You can place kitchen anywhere you like. Only thing is the main purpose what they wanted is before was falling of solar radiation onto the space. So in southeast direction throughout the year you will get solar radiation. That is the one thing that comes onto my mind. Another thing is this northeast, same northeast you will get radiation falling onto from the east side. Like usually the sun, as I told before, in India the solar radiation is like this, and the band varies like. So mostly you to in order to get the morning solar radiation onto the space, people usually recommend that. That's the only thing. And even in northeast, you can see since it is east morning time period from like seven to 11, you will definitely get some radiation from the east. And when it goes to 11 and all, it will be around this 11. You can mark it 12, maybe 7. So this whole range. In order to get solar radiation inside the space, people generally they recommend placing kitchen. That's the only reason. I hope you like try to clear your doubts. I hope it is clear. Let me carry on. Uh, we looked into the concepts of like sound and then sound propagation, and one major concept is the reverberation time. It's basically time required for reflection of the direct sound to die out. Like whatever the sound comes from a source, what time the sound die, like the sound takes to die, like to decay by 60 decibels. If it decays by 60 decibels, it's impossible to hear. So it's a good indicator whether that particular space, or if you just take one single surface at a distance, whether it creates echo, or whether it is increasing the loudness of the space. Yeah, you can use the email if you have any doubts. Actually, there will be another session which will be uh, before, like 2 weeks before the examination, for doubt clearing. During that time also you can contact me. Shall I proceed? You try to ask further doubts in this particular session, like this week's course. Can It's okay that you can always ask any doubts related to the whole course. Looking into this, like imagine your room, have a room, and imagine there is a point source, and then according to, okay, let us, okay, now like I imagine that I'm just opened one face of the room, and then I'm just showing you, like if there's a point source and then the sound start going, like it's a sound whatever it is, imagine it's a omnidirectional sound, it goes in all direction. Let us take one particular sound ray, imaginary one, but it does happen. So if the sound starts getting reflected, hitting each surface, and depending on the surface, the sound might get absorbed also. That is that we will cover further. So this reflection will still happen. Like if there is a absorptive surface on this wall, the portion of the sound will be still be reflected. Like if, imagine 0 to 1, 1 is the full sound that is being is traveling from the point source. It, and like almost zero point 0.6, 60% of the sound gets absorbed, and then remaining 40 gets reflected. This kind of phenomenon keeps happening. So that is the part of absorptivity. This S1 is the actual surfaces area. So using this formula, we try to find what is the to, time that it takes to for the sound to die out by 60 decibels. So this 60 decibel, how it comes, that is actually related to this concept being used. This is a very simple question. You might generally get this problem in the assignment or exam. Next, looking into optimal reverberation time. So, an like very small reverberation time doesn't mean that the room is perfectly functioning well, because depending on each activity in the room, it might be desirable or not desirable. As you can see, this whole this x-axis, this is the reverberation time in seconds, and there is a range of band that is shown, which is optimal for that particular usage. So if you're using the if you're like using we're trying to record like here in recording studios and classrooms, all these places where there is some speech going on, one directional speech, or like some precise recording happening, it is uh, recommended that the reverberation time is as low as possible, so that the sound doesn't get reflected from the surfaces and then it will come back after a period of time. But if you have the if you look into the other places, you have music concert halls and musical instruments are like chorus. These spaces you can see the reverberation time is pretty high because if there is a certain increase of loudness due to the reflection, it will increase the experience of the music. It will improve the experience of the music. So that is heard. So reverberation time, it has a huge range. And if you have like general spaces, like if you have theaters and also normal lecture hall, conference halls, here you have here the reverberation time, it's around swings around 1 for normal conferences and speech related activities. Beyond 1, it's mostly about performance, musical performance related design issues that we have to be solving. All these are like music related, but mostly the speech related ones, they come under this portion, and it's mostly varying from zero point 0.5 to 1.4. You can keep in mind when you are designing spaces, you can try to restrain the reverberation time for the given space within the range accordingly. This is totally to avoid echoes. Next, let us look into the concept of various speech related and voice indexes. One of them is articulation index. It is a very old one, but it's not like used effectively in the field today. But because it doesn't account to reverberation. Articulation is basically a voice level, and it's like ratio between the voice level and the steady background noise. So that is what articulation is. But split intelligibility can be quantified using various metrics like speech intelligibility index, speech transmission index, or rapid speech transmission index. These take into account the reverberation also. And when you look at this table, this will give you an overview. Like if this A is actually articulation index, this is speech intelligibility index, this is privacy index. So here the values vary from zero point 0 to 1 generally, and 0 means it's it will be more effective for a confidential privacy, very silent environment where you want to have confidential speech privacy. And imagine if it's an office environment, it means that only the neighbors will be able to aware what you are speaking and others can't hear. And if we generally have a normal speech privacy, this is more about like in a general office environment, you will be able to hear few parts and parcels of what are speaking, but you won't have a great understanding of what they're speaking about. So that will have an A of point two. And this SI and SIA and AI, they kind of like go along only. And this SIA value is slightly higher than, generally higher than AI value. And looking to speed intelligibility, as the like building consultants and construction people, they add absorption to a room, it approaches a field of free field condition. So this free field condition is like, you have if you add like this is a uh, acoustic panel treatment in the room, you treat, and also this chair what you see, it's a very absorb absorptive porous material type of layer. So this and all will start, uh, it will give an effect of trying to achieve a free field condition, which means that there is not much reflection happening in the space. And why we do it? We do it to quiet a noisy place, reduce the reverberation time, and to avoid echoes, which is a defect. And we also add reflective surfaces also. Example, in the case of concert hall, and also nearest surfaces near speaker to increase the sound output. So it's not like we always try to use absorbing materials, we also use reflecting surfaces also. That you have to keep in mind. And going back to this speed intelligibility, uh, this index, the values are given, and then accordingly you can see like uh, STA index, you have to, it kind of taken in this case it's reverse, like the STA index, one means it's perfect intelligibility, which means that there is no privacy at all. And here, uh, completely unintelligible means you can't hear much. And this, like if we have a perfectly confidential conversation, that kind of environment if we have, we call it as completely unintelligible. And generally we people go for open plan office designs, but it it is not good in a way in terms of noise and speech privacy. And here this graph shows what is the y is the mean satisfied score, and the x-axis we have different types of office plan typology. Like you have a private office room, or if you have open plan office with no partitions or low partition, or you have high partition. This low partition means like 1.2 to 1.4 meter tall partitions, and high partition means like beyond this 1.4 meters you will have high partitions. So you can see in terms of noise level and sound privacy, only private offices people have like voted that they are satisfied with the environment in terms of noise. But in other places, people showed dissatisfaction in terms of sound privacy. Here, generally, so this is just an example to show how if how you treat surfaces, and then in terms of how you provide partitions, you can provide solutions in terms if there's a need of privacy, sound privacy, and noise level. You have to go for one specific approach. uh, next, one more thing is the clarity of sound. It depends on the rate of sound decay. And for if we are finding clarity in terms of speech, the decay is found there. You see, you see with the first 50 milliseconds. But if it's for music, the reflections are calculated for first 80 milliseconds, and this is called Haas effect. So basically, the clarity index, what it measures is the total sound energy arriving before a 80 millisecond threshold, means before and after what is the reflection that is happening, that we try to find out. Because if there is reflection within that small time frame, it will be good if it is for the purpose of music related activities like a concert hall or something. It will increase the it will be helpful in terms of music performance. And here you can see early sound reflection that will support loudness, speech, articulation, and music activity. This is good. Like if we have small rooms, and if you have very large rooms, here you can see this. We have a sound source, and you try to find the reflected distance. The D is actually direct, but ABC is the what is the reflection happening from different surfaces and how it will reach the receiver. So you find the distance like A plus B plus C minus the direct distance B. If the distance is less than 60 feet or 18 meters, it will result in a loudness of speech, articulation, and musical clarity. But if the distance is large enough and it is beyond 68 meters, there will be late sound reflections, and it can create echoes. So this will lead to a defect. So this has to be uh, nullified. Like we have to rectify this defect through design. Like you can provide this reflective panels where you can create early reflections and you can decrease this distance, or you can provide acoustical treatment of absorptive materials which will uh, remove the echo. So in this example, you can see people use these reflective panels to redirect towards the receiver. And a classic example, it's a very old and famous symphony hall. Here, this hall's whole reverberation time has been mapped with distance from source of the symphony hall, which lies in this range, good for concert musical. And let us go into the concepts of how we rectify defects and how we are design, and also we are using materials, how we rectify the noise defects. To avoid the direct reflection, you can use undulations in our like surface level treatment. How the surface is designed, it will lead to diffusion of the sound source. So it's like exactly it works like light only, where you have this kind of coarse surfaces are like different shapes, it will lead to multiple reflection, which is actually the acoustic scattering. Next is there are multiple defects that happen. One thing we generally usually what we talked previously is the echo, where you have a sound source and due to the reflection of the sound, the receiver might receive doubling of the actual sounds from the particular first sound source. This echo, we avoid it by decreasing the reflection distance or by providing absorptive materials. Next one is flutter echo. If you have two parallel sources, the voice keeps deflecting back and forth. This will also lead to a small echo, which is called flutter echo. This can be rectified either by providing absorptive optical treatment or by splaying the surface, making it non-parallel. Next one is the next defect is the focused echo, where if you have a concave surface, it creates two defects. One is focusing, another one is creep. Focusing is like if you are at the focal point. Generally, if you have a curvilinear surface, you will have one focal point. If you are at a focal point, what happens is the point source will reflect and kind of you will receive a kind of a cumulative echo effect. This will result in flutter echo. And creep is something like if you have sound source at one direction and then due to this reflection of concave surface, a particular area will lead to a sudden increase in sound level. So this is called creep. So these also can be rectified using either using absorptive materials or using a concave surface. There are also other effects like excessive reverberance, loudness, acoustic shadow, and resonance. Next, in terms of treating the defects, the material also plays a major role. Here you can see major property what associated to material is the noise reduction coefficient. Since it's a coefficient, it's unitless and addition of all the absorption values at a particular frequency. You add all these and then take an average out of it to find the noise reduction coefficient. And there are different types of acoustic materials. Generally, these are either porous panel and cavity absorbers. And it ranges also NRC also ranges from 0 to 1. And you can see for each purpose they are also suggested absorbing element materials that you can use. And It is very hard to find perfect observers. Mostly here can reach around like zero point 0.9 using sound absorbent banners or thick acoustic ceiling tiles. One example of very high noise reduction coefficient is snow, and going further, as I mentioned, there are three types of observers. One is porous observer, where it contains a perforated material which will observe the sound, and the sound gets like it internally travels and gets reflected within the material, and then it dies out. That's how porous observers function. Next one is cavity resonators. Here what happens is you have a hollow block of body, and then it will have small holes in it, so the sound enters and then it gets entirely reflected and it dies out over a period of time. Next is panel observers. Here you have an impervious material and generally installed onto a solid backing, but there will be a air gap separating the solid backing and the actual panel absorber. And there are like various panel observer. Here you can see example. Here porous observer mounted onto a furring. These are the associated alpha values for particular frequency. Here you can see the absorptive material. It might be very good absorbent for a particular frequency only. So you have to carefully choose the material based on the sound source. So if the sound source frequency is very important, so depending on the sound source frequency, you have to choose. Imagine the frequency is in this range, and then the associated sound, the peak sound goodness for higher range, like around 1000 hertz frequency. It has the so you have to choose the material which has higher alpha value for that given frequency. Here you can see here this material it has 0.82, but if you go for this porous observer, it has only 0.45, but it is a good observer at for sound frequency of 2000 hertz. So this is an important thing that you have to keep in mind. And this sound insulation, we also aim to attain a sound transmission class using this sound insulation. And here you can see these classes are defined based on the type of activity and the space required. And if we like example a laboratory or kitchen, it needs a STC value of 30 or above. And this tabulation shows the various ranges of STC values and what is the actual performance in the description. For example, 40 to 50 is a very good range but not understood. A loud speech heard very faintly, also in this range of 40 to 50. And I wanted to list out few softwares which are associated with acoustic design. These are the list of softwares you can note on. The last one is actually a free tool. Feel free to look into this. Next, we look into lighting. So when we talk about lighting, the first thing, the source. So the light and what range it belongs to. Light is basically a electromagnetic wave which falls under this range, visible light range between 380 to 780 nanometers. So this is the only range we can be able to see. And here is the session showing various other electromagnetic radiations and what is the range the visible light belongs to. It's basically a very narrow range when you consider the whole electromagnetic radiation spectrum. And there are few terminologies that you have to keep in mind when you look into lighting design. First, let us start with the source. Luminous flux is basically it's about the light source, the total amount of light being emitted by a light source. It is measured in lumens. And there is another concept called luminous intensity. It's basically light flux emitted by a light source in a particular direction per unit solid angle. So this conical illustration in this diagram, this shows the luminous intensity, and once the light source is there, there will be the light source will fall on a particular surface, right? And this is measured as illuminance, the amount of luminous flux from a light source falling on a given area. It's measured as lumens per meter square, generally called as lux. And what we, the human eye, perceives, the light that the humans perceives due to the reflection from the surfaces, all this, that is the luminance, the ratio of luminous intensity of the surface to the projected area of the surface, which is its unit is candelas per meter square. There are various parameters that influence the quality of lighting comfort. Here we talked about illuminance and luminance, and there is this concept of glare, spectral energy distribution, color temperature rendering, and flicker. Here, this glare, flicker, are defects which we try to avoid, and this spectral energy distribution, color temperature, and rendering, these are light quality parameters which we have to selectively choose from. And luminance and illuminance are these are basic parameters. We kind of set a benchmark illuminance level for a particular activity and try to achieve it in general case. Next, we look into daylighting. Daylighting is basically uh, the light that we receive because we due to the sun, solar radiation, and it should not be confused with solar radiation. Solar radiation is a heat component. Daylighting it generally just takes the lighting part, the luminance. So daylighting generally it improves the light quality and also increases the uh, occupant comfort and also productivity, and it generally goes along with uh, daylighting is, since it is available only during the daytime period, and based on the building design you can achieve the lighting comfort using just daylighting, but and also you can use auxiliary lighting. So you have to design in such a way that you reduce the requirement of auxiliary lighting during the building occupancy period. And design sky illuminance is the illuminance uh, that the location is. It's a location related concept. It's a particular location. What the what the location receives the 80% of the time between 9 a.m. and 5 p.m. on a horizontal surface. So this concept is mainly dependent on the actual latitude the place is belonging to, because the values keep decreasing as you go away from the equator. So one of the key daylighting related uh, concept is the daylight factor. It's basically the ratio of the illumination indoors with respect to the illumination outdoors. It's like so here this is also a factor. Next, speaking about the, as we mentioned, glare, it is the effect of brightness or the brightness differences within the visual field, which causes annoyance, discomfort, or loss of visual performance. So generally, it's the due to light, you kind of get discomfort or irritation. Like, try to avoid glare as much as possible. So there are two types of glare. One is discomfort glare. Another one is disability glare. Discomfort is glare is basically, as the name suggests, it kind of creates some kind of level of discomfort, but there won't be full uh, loss of the sight due to the glare. But disability glare, it kind of creates a loss of visual performance totally. And when we look into lighting, there are two different uh, parts. One is the diffuse lighting, another one is direct lighting. Direct lighting is due to we have a single point source, it will on a particular object, it will create this direct light and then it will create sharp shadows. And there is but if you have uh, lighting coming from different directions, it will create very less or it will create soft shadows, or like there won't be shadow at all. In the case of like if you have an overcast sky, what happens is the imagine this sky and this is the surface. What happens is if you have the overcast sky, the light from the source, which is the sun in our case, gets internally reflected, and then the light comes from almost every direction. So if there is an object on the uh, plane surface, what happens is you receive, since you receive light from all the direction, there is very soft shadow or there is no shadow at all. What it is. Next, let us look into artificial lighting concepts. Artificial lights basically they use convert the electrical energy, and they usually it's what happens is it heats up an element to an excited state where the element will start emitting radiation, electromagnetic waves. And since some few metals they emit the radiation in the visible spectrum, so using this concept, we this artificial lights they emit visible light using electricity. So here this luminous effect plug efficacy is basically what is the ratio between the light output and the actual energy used. So it's basically the unit is lumens per watt. The lumen is the, as you know, the lumen is the light output. This is the power input. So for every given watt of power, what is the lumen output? Next is the color rendering index. This is also associated with the uh, light source. Here, if you have a light source of this can be daylight or also artificial light. Here, generally daylight it has almost color rendering index of 100. So having a color rendering index of 100, what it means is that you have a spectral output that contains the entire visible spectrum. So it basically renders all the colors accurately within the visible spectrum. And if we have like the case of example, you have low pressure sodium lamps, it has a very poor color rendering index where you will mostly it falls, it will slow pressure sodium lamp, it will give out a color like yellowish toned color output, as we generally see in street lamps. But if you have a good LED lamp, it almost has a color rendering index of 90. which means that almost like 90% of the visible spectrum range is being emitted by the light source. Next concept is the color, correlated color temperature. So based on the color temperature, you kind of name the type of color as warm or cool tone. So if you have temperature color temperature beyond 4000 and above, it will result in a cooler color temperature. If you have like temperatures around like below 3000, like 2800 to 2000, they they will have a warm color temperature. It's basically a method of describing the apparent color of light that is nearly neutral. Like it it won't emit like exactly blue or yellow color light, but it will be almost white, but it will be having a tint of blue or yellow. So daylight factor example the outside illuminance is 8000 and the room average illuminance is 240. So daylight factor you just take a ratio out of them, then you will get the daylight factor. In this case it is 3%. And there are also other associated measurements, lighting measurements that you can incorporate in the lighting design. One is daylight autonomy, which is the percentage of annual daytime hours that a given point in space. Example, that's a particular point. What is the percentage it is attaining? So here, 53% of the whole floor area is above 50% of the daylight autonomy value. So here you have to fix a particular illumination value. You check whether that particular point is attaining over a particular duration. And useful daylight illuminance, it's more like it actually has a band of values instead of having one particular value and checking whether it is beyond that value. Here it has a particular band where it ranges from like here in this case it ranges from 100 lakh to 2000 whether what percentage of floor area is having at least 50% useful daylight illuminance over the period of time. These are few useful lighting measurements, not which you can utilize when you design the spaces. So you can use various lighting softwares. Nowadays they come along with softwares. Example in this case, previously would have been told about design builder. Design builder also includes few lighting design analysis also. Next, let us look into few example questions. Laboratory testing of STC in general does not account for, it doesn't account for flanking transmissions. Articulation index below zero point 0.2 would indicate basically it will sorry, less than zero point 0.2. What it indicates is indicates speech privacy. So if it goes beyond 0.4, like go over a limit, it means that there is no privacy at all. Clarity sound is expressed as a ratio of sound energy arriving and before and after a time threshold. It's either like 80 ms or TMS in general. This is for music, for speech. Room mode is a factor of room dimension. Next, we have a con concave wall surface. So what it will lead to? So flutter echo is basically it's due to parallel sound source. So concave, if we take one is this focus focusing of sound. Another one is creep. So both focusing and creeping will lead to impedance tube method is used. It's used to determine the sound absorption. So basically sound for materials we generally measure only sound absorption. Using this we find sound absorption of materials. Then further we can also find the NRC value, which is basically an average of alpha for different frequencies. Performance of Helmholtz reference resonators they depend on so all these the absorption, the cross section, and also STF sound. NRC is expressed as so generally it's an unitless fraction. Define skylight illumination varies with said before it is depends on the latitude. So depending you have the globe, so the equator will receive the highest illuminance around like 1000 K lux keeps decreasing. So it varies with latitude only. Open loop daylight controls basically they are like open loop and closed loop daylight controls. Open loop only considers the daylighting part, so it's basically natural light. Yes, I'll close the session. Thanks for joining. Those who have not joined, hope you uh, like the session. So this is the last doubt clearing session in this subject, and mostly you will be having your examination in the September month. I think it is 24th of September. Hopefully, there is another doubt clearing section. If you have any problems having doubts, you can ask in that session. And all the best for your exams. Thanks for joining.